Hey guys, welcome to the next video on SN1, SN2, E1, E2 stuff. So this video is going to be focusing on how do we decide now with what we've learned, what will be an SN1, SN2, E1, and E2 reaction, okay? Now this is, people consider this complicated in the beginning, but they tend to get it with more practice. Now, one thing I will say beforehand, you will see a lot of charts floating around, whether found online about about how to decide between SN1, E1, SN2, E2. I'm going to say right now, be very careful with these charts. They do not always work. I have seen many questions where there are exceptions, and that if you use these charts, it will just not help you. Usually in the test, there is always at least one question where they will force you to now use what you know to decide between one of these. It will not be something you will find in any of these like decision trees or flowcharts, stuff like that, right? Because they want to see if you can think, not read off of a chart. So I personally did not go into exam 3 with any of these charts on my card. The only chart I would consider as saying it would be a good thing to put in your index card is what's considered good nucleophiles, good bases, stuff like that. That could be useful, especially for the weird stuff like, CN minus or N3 minus, stuff like that. Weird stuff that you haven't seen too often. That's okay. But I'm going to tell you, if you're relying on these charts to get you through exam 3, it's going to be very difficult. You will probably not get a mug. It's going to be very hard to get 100. I'm not saying impossible. It's going to be hard. But most importantly, you're not learning the thought process required. This is really the first thing in Orgo that is going to require you to think deeply, and you actually understand Orgo to do well in. Orgo 2 is only going to get worse in terms of being able to understand reactions, okay? So I would say try to get into the mindset of understanding and thinking through Orgo. Don't memorize. Memorizing can only get you so far, but it will be very hard to get an A, all right? So please try as hard as you can to actually think in terms of just use your thought process. Understand the basics of these reactions and you will understand how they work, okay? People say that this is a very complicated topic, and I'm not going to lie, initially it is, but it is not as hard as people make it out to be unless you're relying on charts, okay? So that's what I wanted to say right in the beginning, okay? And in my problem sets, I will purposefully take questions where these charts do not work. Of course, there will be some questions where the chart can help you, right? These flow charts. But a lot of questions I am going to purposely put to show you guys where these charts break down, all right? Now, of course, you could correct by putting those stuff in your index cards, but again, I am sure they know how to get around you putting something on your index card, all right? So let's get started. The very first thing you need to use when deciding substitution or elimination, SN1, SN2, E1, and E2, is the substitution pattern of your alkyl chain. All right. Now, when I say substitution pattern, I'm not talking about SN1 or SN2. I'm talking about how when we talk about primary, secondary, tertiary carbocations, right? That's what you need to be looking at, right? Or actually, more importantly, the very first question is, do you have a good leaving group? If you do not have a good leaving group, we can't immediately go off of what we're doing here. In the future, I will talk about how we get around bad leaving groups. Okay. But the very first question you should ask, good leaving group? Okay. So hopefully your answer is yes. So a good leaving group, remember, we talked about this in the video, something like the halogens Br, Cl, and iodine, right? Alcohol groups are not good leaving groups, right? We talked about a way to make it into a good leaving group, but I'm going to omit that for now, all right? We will come back to it in the later videos, right? So hopefully you have a good leaving group. The next question is your carbon where the leaving group is attached to sp3? None of these reactions work if you have a leaving group off of an sp2 carbon. You cannot do any of these reactions, okay? So you must have fully single bonds on your carbon of the leaving group, okay? So hopefully, again, your answer is yes. If not, well, then you can't do these reactions. All right. Now that you've said yes, you need to identify if your carbon with the leaving group is primary, secondary, tertiary, or a methyl group. Okay. So we have your good leaving group, right? That's the first question. Yes. Okay. Question 2, sp3. So we said yes. All right. Number 3. So you have a methyl, primary, secondary, or tertiary substrate. So similar to talking about carbocations where this would be secondary. If we had a, having something like this would be primary, tertiary, and then the methyl, same idea here. Just replace the carbocation with the leaving group. So if I change this carbocation to Br, that's a secondary alkyl bromide, primary alkyl bromide, tertiary alkyl bromide, and now a methyl alkyl bromide, right? And so that's how we talk about primary, secondary, tertiary, methyl. Sorry guys for the noise, there's people walking in and out of the chem library. Okay, and so that's the next question you need to ask yourself, because it can simplify a lot of stuff, and you'll see why in a second. Okay, so let's say you answered methyl, right? So this scenario here, right? Your leaving group is all connected to one carbon, and that carbon doesn't have any other carbons connected to it. So using that knowledge of what a methyl with a good leaving group, so Br, chlorine, iodine, right, is, what of the 4 reactions can we already rule out? Well, how about elimination reactions? I mean, elimination reactions form double bonds. We can't form a double bond to kick our leaving group out because we don't have another carbon to form the double bond with, right? So right off the bat, you can see that using some logic, we can see if you answer methyl, we can eliminate E1 and E2. So now the question is, all right, what about SN1 and what about SN2? Which of those two? Well, remember the SN1 mechanism, we get a carbocation. So I would have a methyl with a carbocation. We know the carbocation trends, right? You see all this stuff is coming back. This is why it's a good idea to understand rather than memorize, because people have a hard time when they start combining concepts, and it's only going to get worse as you get into Orgo 2. So we have a methyl with a carbocation. Well, we know that when talking about something like carbocation stability, the more substituents, the better. Tertiary is really stable. Secondary, a little bit less. Primary, not that stable. Methyl, no carbons whatsoever, really unstable. So if we have a really unstable carbocation, well, then it's just not going to form. But SN1 requires a carbocation. So if the carbocation won't form, we won't get SN1. So that leaves us with one option, that a methyl alkyl, whatever, with your, is a methyl with a good leaving group on it, will always go SN2, right? Makes it much easier, all right? You can see that you thinking it through, you can justify it, and it makes sense. At least I hope it's coming across that it's making sense to you guys. I know this topic is very relatively, it's pretty difficult. I'm not gonna lie, to understand initially. I did have a hard time in the beginning, but I started, I looked at these charts in the beginning and it was throwing me off. So once I moved past the charts and started thinking my way through them, it got much, much easier. All right, so that's a methyl situation. So we got 1 out of the 4 done. All right, that's the easy situation, and we can know that rule out E1, E2. Then we can rule out SN1 because the carbocation is just horrible. All right. So therefore, no matter what you're reacting with, doesn't matter if your nucleophile or your base is good, bad, bulky, doesn't matter. it's always going to be SN2. I could have Cl minus. I could have Cn minus, OCH3 minus, H2O, CH3OH, terp butoxide. Doesn't matter. As long as it's a methyl, you have SN2, period. Okay? So that should be relatively clear. Now, let's go to primary. All right? A little bit not as straightforward, but still not too bad. All right? So we went the primary route. So, right, primary. Okay. Now you can see I'm writing sort of like a flowchart. Do not rely on this. Even this chart that I'm writing will break down in the future when they give you those kinds of questions I mentioned earlier. I'm just trying to show you the thought process. All right. So now we have a primary. Now we have to think of how it would work now.
Thank you, bro. Thank you.
So now let's think, how does the primary work, right? So let's draw a primary alkyl substituent. So here, just do BR. All right. So we have it off of a primary carbon, and remember, if that whole primary thing is confusing you, just think of how a carbocation would look if we called it primary. Okay. So we have this primary Br, right? Any good leaving group, and so now what we had to ask ourselves was, okay, can we rule anything out, right? Well, think about SN1, E1. They go through carbocations, right? Remember, the mechanism is always the same for both, is in the leaving group leaves. So we get a primary carbocation, right? There's a methyl there, just so it's easier to see. Okay. Well, is a primary carbocation stable? It has only one carbon substituent, right? That's not that great, right? Secondary is moderately stable. Tertiary really is pretty good. Primary, not really. It's a little bit better than methyl, but still pretty garbage, right? So it's not that stable, so it's not going to, the leaving group isn't just going to leave to form the carbocation. So right then and there, we can already eliminate any of the reactions that form a carbocation. So SN1 and E1 are out. So now we're just down to SN2 and E2. So you can see, logically going through this is actually what's going to get us through these questions, all right? And of course, practice is always going to make it better. So we've already eliminated any of the carbocation reactions. So now we're just down to SN2, E2, right? So now, how do we decide? Well, the substitution alone isn't going to tell you anything this time, okay? It's not going to help you. What we have to do is we have to examine what we're reacting with now, okay? So we draw this here. So now we have to think of what we're actually reacting it with, right? So the question I would ask myself now is, well, what do I have? Am I reacting with something like H2O, or am I reacting with OCH3 minus, right? Okay, that's going to help you answer this next question. Now, how exactly is this going to help us? Well, let's look at this primary right here. I'm going to react it with OCH, okay, OCH3 minus. All right, thinking back to the last video, we know OCH3 minus is a good nucleophile, but it's also a good base. Substitution reactions prefer nucleophiles. They use the ability of the compound, like this reactant right here, to be a nucleophile. Elimination reactions prefer the basic component. Okay, so like I said, we can have a nucleophile that's a good base and a good nucleophile, right? So they would prefer, so the elimination reactions prefer it to be a base, right? Whereas substitution reactions prefer it to be a nucleophile, okay? So OCH3 minus, or something like OH, they are good nucleophiles because they're small and they're good bases, right? So Well, now still, this doesn't really help us too much. Is it SN2 or E2? So now what the predominant factor, and I haven't said this before, all right, so this is going to be new. SN2, right, is not, what do you call it, relies on a factor kind of called steric hindrance, right? I told you that the nucleophile has to get in really close, right? It's got to get in super close to our substrate. It is going to be much easier for an SN2 reaction to happen on a methyl and a primary when we have very little things surrounding the carbon with the leaving group versus something like this, where it has to get past all these methyls coming from the back, hit that Br, getting past two of these methyls with their hydrogens and all that stuff, right? Which means, therefore, SN2 happens with the less amount of substituents on our substrate. Methyl was amazing because, well, we had no other option in general. Plus, there's just no substituents, period, which is great for SN2. Primary is the next best option for SN2. All right. So, on a primary leaving group, right, regardless of whether you have whether your nucleophile is a base or not, a good base or not, you are going to go SN2. Except in one condition. So SN2 would look like this, right? Because SN2, like I said, the real limiting factor of SN2 is the fact that the substrate, what we're attacking, is bulky. The bulkier it is, the worse it's going to be for SN2. The less bulky or less hindered, the better for SN2, right? So we only have one substituent coming off the carbon with the Br, right? Remember, we don't consider the Br a substituent. We consider that carbon a substituent. So that's perfect, right? So that's pretty good for SN2. Now, like I said, there is one case where this does not work, right? And that's if I had this compound, something called a bulky base. So remember, it's an O with a minus charge. So we've talked about this as a base before, and I've called it a bulky base, it's terbutoxide, right? But what about the nucleophilicity? Well, we talked about that before too in the last video. This is too big with those methyls to get in. It's very difficult for it to get in there. So even though it's got that negative charge, it's just too big, okay? So what would happen instead is you will get an E2, all right? So you can get an E2 here instead. Because remember, we narrowed it down to SN2 and E2. We knew that carbocation reactions won't work, so SN1 and E1 out. But we were able to narrow it down to SN2 and E2. And we'd only do E2 in the event where our whatever we're using to attack is bulky. Okay? So the fact that it's bulky really makes the nucleophilicity of it go down. But it's still basic. Because think about it. It's much easier to grab a hydrogen from here, where there's not much stuff around it, versus coming into this with this already bulky substituent and getting past that methyl. Those hydrogens are much more exposed. So what would instead happen is O minus grabs the H, this bond collapses, remember E2 is in one step, and this bond breaks out. So we're going to get, hold up, 2C, and then CH2. Remember, there were two carbons here. 1, 2. I probably should have just made the chain a little bigger to make it easier to see, but I'm sure you guys understand it. And if not, of course, always speak to a TA. They'll understand, or email me. I'll be happy to clarify. All right? So we've pretty much said that SN2, the limiting factor is if your nucleophile is sterically hindered itself. That means your nucleophile itself is bulky. Or if your substrate itself is bulky. Okay? So let's summarize so far. Methyls are always SN2. Primary is always SN2, except if you have a bulky nucleophile or base. Okay? Now, I said that these charts break down. And it will break down exactly at this idea that for primary you'll only get, let's say, so here, drawing this example, right? This is a carbon here, and it's got 3 other carbons right there. 1, 2, 3, 4th, and we have Br. Br is on a primary carbon. Now imagine I reacted with OH minus. So I'm not talking about the one bulky base scenario. I'm talking about this. Using what we know, we'd say it's an SN2 reaction, right? Nope. This is where the charts break down. This is something called beta branching. The carbon with your substituent is called the alpha carbon. Sorry, with your leading group. So alpha, that means that's beta. If you have the more branching on that beta carbon, the harder it's going to be for your nucleophile to act. So if I drew, let's say this, it's only 2 methyls on there, it's going to be easier for that OH minus to get in there versus the full branching of 3 methyls. So you see, if I use that little idea that I just had with that flow chart, sort of that primary with anything but a bulky base is going to give me SN2, well, it's not going to work. SN2 is actually not going to happen really at all in this situation, right? And this is a question similar to what I put in your problem sets, and I haven't finished it, so it's not released yet. It will be. But yes, this is the idea called beta branching. Very important for the test. Very important, okay? Look at exam 3, 2018. It was something very similar to that. And so yeah, so you can see here that these charts don't always help you. But the main point I'm trying to get is the thought process. These little details can be learned as you do practice problems, right? So now if you also had this primary group and we acted with something that isn't a good nucleophile maybe and not really that good of a base, as long as it wasn't a bulky base, you will still do SN2. So H2O comes in and attacks here, kicks the Br out. Plus, and then this gets deprotonated, so we still get OH. So really that only E2 thing happens when you have that bulky base for primary. All right, so a little bit more complicated than a methyl, but hopefully not too bad. Again, practice. Taking notes can only get you so far. It's a good idea, but the practice is where you need to be. Okay, so that's covering methyl and primary. I will end the video here and finish secondary and tertiary in the next video. All right, and this will get us through the general thought process of substitution elimination reactions. Okay, and after that we'll cover a little bit more of like the little details. All right, so like solvents are a little bit over exaggerated in terms of how important they are, but they can sort of push your reaction in one direction. Okay, and also the idea of how temperature plays into effect. Now I know it may sound overwhelming, but you guys with practice is where it's at. All right, these flowcharts will help you in the beginning, but when you practice it, you'll realize, well, I'm not looking at the flowchart anymore. I remember it, and more importantly than that, I understand it. All right, so that's what I'm trying to get you guys to do. I'm trying to get you guys to really understand it, because then you could answer those tricky questions that I call them mug busters. They're designed purposely for students who memorize or write charts and stuff like that, because they put a concept that if you don't understand, it's going to mess you up. Okay? I hope that everything here made sense so far. I know it's a little bit overwhelming. Please ask questions. Email me. Go to the TAs. If you're on YouTube, leave the comments so that I can answer it for other people who also have this question. All right? Ask on the Facebook group me, wherever. And please make sure you understand this. All right? It's going to be the majority of your exam 3. Right? This is not something you don't want to be able to understand. Okay? So I will see you guys in the next video where we'll finish out this little thought process tree. Okay? Hope this all makes sense.